Okay, there we go. Mirror symmetry and big algebras.
It's a new presentation.
No, we're going to do that later. Yeah.
Okay, so thank you. It's a great pleasure to be here and talk in this conference. And because of the subject of the conference, and because I was given the opportunity to speak longer, I thought that the first lecture I'm going to give a sort of survey for mirror symmetry for Langlands dual Hitchin systems, and the way how I have seen it, and then this will lead up to more recent work with Nigel Hitchin, and then next time I will talk about the baby form of these big algebras, and then all the various ingredients which go into their study, equivariant cohomology and Kirillov algebras. And then I will also show you how the spectral curve picture of the BNR correspondence somehow geometrically emerge from this from these mirror symmetric considerations. And in the last lecture, I will talk about these big algebras, which by now I'm very excited about, and they are in themselves, I think they are very interesting. But the whole series of talks will be to explain the motivation behind them, how they come from mirror symmetry, and maybe at the end I will also discuss how real forms and involutions coming from real forms act on the big algebras, and then I have made recently some conjectures, so I will talk about those at the end. So today I will give a sort of survey, very schematic, not at all well defined. I mean, the motivation comes from physics, so it's not a proper mathematics. So first, let me just give you this. I mean, some of you might have already heard me speaking about it. It will be pretty just bringing back up the ideas of mirror symmetry. In fact, when I was in grad school, that's when it was trying to be very important and very exciting. So I was learning about mirror symmetry in grad school, and so these things happened before my PhD. So it was, of course, it comes from physics, from string theory, and when it really hit mathematical interest was this work of Candelas and De La Ossa, Green, and Parks in 1991, where they made some incredible predictions in enumerative geometry using these convolutive ideas of mirror symmetry. And of course, you must have, all of you have seen it. So mathematically, mirror symmetry is very, very interesting because it relates two different geometric aspects of two Calabi-Yau manifolds, X and Y. So on one side, we will be studying the symplectic geometry of the first Calabi-Yau, and its mirror will be carrying its complex geometry. And then this two different subjects which are pretty different. One is very algebraic geometric, and the other one is more topological differential geometric. Somehow have at their heart some amazing common structures. So already before maybe even these curve counts, which was the one which hit the mathematical interest, before that physicists had identified that originally it was what Calabi-Yau threefolds, that this mirror phenomenon the first easiest aspect of it is the topological mirror test. So for them, again, it was Calabi-Yau threefolds in the beginning, and they found several mirror partners which satisfy this topological mirror test. The Hodge numbers of one relate in a funny way with the Hodge numbers of the other. This may also be the origin of the word mirror, because if you look at the Hodge diamond and then you take this unusual symmetry axis and then you flip it, you get the Hodge diamond of the other. So that's somehow the easiest. And then actually very, very early on, which is kind of amazing, there was a mathematical conjecture not quite well defined, but which has been really the mathematical driving force to understand this phenomenon. It implied, in some sense, those enumerative predictions of the physicists, but it was bringing in the language of homological algebra, and it related now two derived categories on the two sides. On one side, we have the more familiar derived category of coherent sheaves on one of the Calabi-Yaus, and on the mirror side, we have something yet to be defined. Even today, I'm not sure how exactly we have this defined, how much generality, but the Fukaya category of a symplectic manifold was in fact developed, motivated by this conjecture, so that this holds. So what we need to know about them, maybe only one thing, is that a typical object in the Fukaya category is a Lagrangian, sometimes together with a local system on it. And then, of course, the other side, you will see completely different coherent sheaves, which could have all kinds of complex dimensional support. So it's really surprising that these two kind of geometrically very different categories might agree. And then again, it was quick succession in the beginning, and that was when I was in grad school, 1996. There was the first time when there was a construction and a suggestion on how you might be able to construct a mirror of a given Calabi-Yau. Back then, before that, it was just many examples, but there was no intrinsic way to relate one with the other. And we will see in our situation how that works. So, okay, I just say this, so that mirror symmetry is still one of the central subjects in modern, I don't know, symplectic algebraic geometry, and it's still not completely understood. Still, I mean, this is much more, of course, by now we have Gross Seibert program, many aspects of mirror symmetry we understand very well, but still there is work to be done there. And was very interesting that for the moduli space of Higgs bundles, the total space of the Hitchin system, somehow mirror symmetry naturally arose from the Strominger-Zaslow proposal. So let me show you how this is happening. So again, it will be very sketchy. So we take a smooth projective complex curve. For this general story discussion, I will take a complex reductive group, and then its dual group, which basically, when I will concretely talk about things, it will be always PGLN and SLN. And then Nigel, a long time ago, has constructed a gauge theoretical way the moduli space of stable, semi-stable Higgs bundles, and then by algebraic geometrical methods was construction by Simpson. And this moduli space will be the main player. This will be one of the Calabi-Yaus. Okay, and I just say a few words at this point about what the Higgs bundle is. I'm sure most of you have seen it. So, but it's what's interesting, and this will be crucial in what we are going to at the end go, is that a Higgs bundle, we will talk about G Higgs bundles for a general reductive group, is a principal G bundle together with the Higgs field, and the Higgs field is a section of a vector bundle. So E is originally not a vector bundle, it's a principal G bundle. And then we take the adjoint bundle of the principal G bundle, that's a vector bundle, and then we twist it with the canonical bundle. And we will think of this as some sort of Lie algebra valued function on the curve. Okay, and then the major player, of course, is the Hitchin integrable system, which you can very quickly, abstractly, you can say that the map itself is nothing else but the affinization of the total space. That is, you take all the algebraic functions on the Higgs moduli space, and it turns out to be finitely generated. And then you will get the natural map to the spectrum of this finitely generated algebra, which turns out to be proper, and that's the Hitchin map.
it's a proper and amazingly a completely integrable Hamiltonian system. So there is a natural symplectic form on the moduli space, so that with respect to the fibers of the Hitchin map are Lagrangians. And then mirror symmetry, as it will appear for us, it actually is not in this complex structure, but another complex structure on the same manifold. So it turns out that there is a full two-dimensional family of complex structures, natural complex structures on the moduli space. Namely, there is a hyperkiller metric. In complex structure I, we have this moduli space, this complex manifold. But in complex structure J, there is a different moduli problem. And the original mirror symmetry is actually about that complex Calabi-Yau manifold, the moduli space of flat G bundles. And so what we noted with Michael Tadeusz, but it was actually Nigel who pointed to me to the paper of Strominger-Yau-Zaslow in '96, just after it appeared, saying that it looks like the Hitchin system, even though those are not Calabi-Yau threefolds, but they are still Calabi-Yaus, and then they should satisfy the Strominger-Yau-Zaslow conditions for Langlands dual groups. And indeed, we managed to prove with Michael that for PGLN, you have from the M-deram moduli space, you can take the Hitchin map. Of course, after changing complex structure, you can take the Hitchin map, and here on the Langlands dual side as well, the two bases of the Hitchin systems are naturally identified. And then by changing the complex structure, these originally holomorphic Lagrangian fibrations become special Lagrangian fibrations, and they have generic fibers which are dual special Lagrangian tori. And this is exactly the recipe. That's what SYZ said, that given a Calabi-Yau, you should find such a special Lagrangian fibration, dualize it, and they don't tell you what to do at the singular point. So that's why for them it's kind of still difficult today. But here somehow we are given on both sides the two fibrations, and amazingly we are given an example of the SYZ picture. Okay, the difference is that these are not Calabi-Yaus but hyperkiller varieties, and also they are not projective. They are semi-projective, so quasi-projective, proper over an FI space. But other than that, the rough geometrical picture is similar. And so then with Michael Tadeusz, we were trying to find some sort of enumerative consequence of this potential mirror symmetry. And so we started with the easiest one, the topological mirror symmetry, and we asked ourselves, is there a formulation of these Hodge numbers? Or we looked at SNN and PGLN moduli spaces, so that these Hodge numbers, well, what we found that they were matching because of the non-projectivity of the varieties. You wouldn't expect immediately the same kind of flip like you do in the topological mirror symmetry, although later with the relative Hadlefshets, you could actually explain that there is a symmetry similar to that as well. Okay, and so, okay, I'm not going to define it now. It's just some sort of non-trivial construction of Hodge numbers. Even it's funny because it's for differential geometers, these Hodge numbers are not really understandable, but it's algebraic geometers, Delin, who have described this, and then we use also stringy Hodge numbers on the PGLN side. So it's a lot of machinery goes into it so that it actually works. And that then we conjecture that this is always the case, and we had been able to check it in the low dimensional cases. Okay, and so the way how I look at this, that this mirror symmetry somehow is already manifest in the topology or the geometry of the stable moduli space. You will see in a moment that if you push this mirror symmetry idea, you will be working with stacks. And somehow this is the first place where it seems like that the semi-stable moduli space is captured the mirror symmetry. And yeah. Okay, and then later I noticed similarities with Ngo-Bauchau's proof of the Langlands Langlands fundamental lemma, where he has reformulated some combinatorial statement about orbital integrals in terms of cohomological statements about the cohomology of Hitchin fibers with this stringy Hodge number business. And I was hoping that one can use actually his techniques to prove this. And then it was very interesting, surprising to me that Grassmannian, Gris, and Ziegler came up with a very different idea. They used, again, an arithmetic technique to prove topological mirror symmetry without any use of the machinery of Ngo. And so that was the first important result of them. And then they turned this argument backwards, and they have used the same techniques to actually prove Ngo's geometric stabilization using periodic integration. So I find this the most exciting application of these ideas, motivation coming from physics, but then you prove something important in number theory, and you use relatively simple arithmetic techniques to achieve that. And satisfactorily, in fact, Maulik and Chen recently have managed to carry out my original proposal to prove topological mirror symmetry using Ngo's technique. So now this is a complete story. We have, this is a theorem, the topological mirror symmetry. Okay, great. And then let me now go on to the next level. So you remember the next level for us was this homological mirror symmetry. And for that, we had to wait for physicists to have a very extensive work on, okay, this is a physics paper, but with a lot of mathematical ideas. And they derive this homological mirror symmetry between these mirror symmetric Lagrangian Hitchin systems from S-duality in 4 dimensions, from certain Young's theory there. And so their argument is kind of non-trivial. So homological mirror symmetry would say that the derived category of current sheaves on one of the Calabi houses isomorph is equivalent with the Fukaya category on the mirror side. And then they go on, and this is again always the Fukaya category is the difficult thing to define and study, especially with these kind of open spaces and sometimes singular spaces. Anyway, they make some physical arguments to say that that this category should also be equivalent with the category of D modules on the. Well, now they actually move to stacks over stacks of G-check bundles on the curve. And why it's really interesting. So that means that this category should be equivalent with this category, and this way, using these physics ideas, they have recovered the rough form of Beilinson and Drinfeld's geometric Langlands correspondence. So that was this new angle to this mirror symmetry gain. Some hardcore Langlands correspondence was at least conjecture. I mean, there are many conjectures here in physics arguments. For us, we will use a simplification of these categories. There is a natural way to deform both sides of this proposed equivalence, and that we call the classical, or Donaghy and Pantev call the classical limit of homological mirror symmetry. So here you can put into lambda connection moduli space these flat connections, and this way you can degenerate the flat connection moduli space to the Higgs moduli space. On the other side, you can somehow dequantize D modules to get coherent sheaves on the cotangent bundle, and you would get roughly, or that's the argument, you would get the now symmetric statement that the derived category of current sheaves on the Lagrangian Hitchin spaces should be equivalent. Okay, that's was their derivation, but they really, of course, had more, because now we have dual abelian fibrations over the same base, and generically they are actually abelian varieties, smooth in particular. So you have a Fourier-Mukai transform on the generic fibers, which is an equivalence of derived categories on the generic fiber, and over the dual abelian variety, which turns out to be the same as the dual fiber. And so when you put this Fourier-Mukai transform in a family over the smooth locus at least, you would get an equivalence. And so that's a motivating heuristic that we use when we think about mirror of objects under mirror symmetry, that generically, at least it should be just Fourier-Mukai transform. And then Fourier-Mukai transform had been extended into the integral spectral curve locus. So and some of the work actually can check things there too, but not, of course, completely over the whole base. I mean, my main interest is always the nilpotent cone, the fiber over zero, the most singular fiber, non-reduced. And there we don't yet have even a slightest hint of how this Fourier-Mukai transform may work there. Okay. And then, okay, so this was like a long time ago, but actually it's still the same paper. Kapustin and Witten paper in 2007 has argued that this is not just mirror symmetry. So it's not just the agreement of the A model and the B model, the agreement of these derived categories, but it comes from 4 dimensions, this mirror symmetry. So therefore, it will have enhancements. So let me talk about these enhancements of the mirror symmetry, which both aspects were already introduced in the paper of Kapustin and Witten. So one actually is the hyperkiller aspect, that we have hyperkiller varieties, not just Calabi-Yau ones. And so in fact, we have, you know, an S2 worth of complex structures, which we just simplify to I, J, and K. And then the physicists are arguing that you can think about these brains, which I haven't, which I'm not going to talk about much, but that behave like a coherent sheaf in one of the complex structure, but more like an object in the Fukaya category in the other 2 complex structures. That would be a BAA brain. And they argue, again, on physics basis, that a BAA brain should be mirrored to a BBB brain, which is mathematically easier, perhaps, to understand. Is a trihomomorphic vector bundle on a hyperkiller submanifold. Okay, there is one category of BAA brains which are simple mathematically too, and these are just complex Lagrangians, holomorphic Lagrangians on the Higgs moduli space, because with respect to a Higgs moduli space complex structure, these are holomorphic, and with respect to the other 2 complex structures, they are Lagrangians. So that's one class, and there are plenty of these Lagrangians. I will also discuss some later. And what's mathematically the interest here maybe is that physics tells us that to each of these complex Lagrangians, for example, there should be a mirror object, which is proposedly a BBB brain, a triholomorphic thing, which, as far as I understand, it's a much more rigid, mathematically, much more rigid object. It's like a hyperkiller. Okay. So let me show you some examples where this works beautifully. One of the first mathematical examples were in Nigel Hitchin's in Nigel's work. He looked at real forms of, in this case, actually it's GL2n, should have been GL2n. And that's a Lagrangian famously. These players will come back later, and I will talk about involutions. So there is a natural complex Lagrangian inside the moduli space of Higgs bundles for any real form on the complex group. And UNN is special because it's a quasi-split real form of Hodge type of GL2n. And Nigel, so therefore it's a BAA brain, and Nigel found a nice candidate for the mirror, namely the Dirac bundle. One of the few constructions of known constructions of hyperhomomorphic bundles is this hypercohomology construction of the Higgs field, which we can call Dirac bundles. But what's interesting is the support. Again, this we should be having here GL2M, but the support turns out to be in Nigel's work should be SPM inside GL2M, and he does give some evidence for this observation, and I see we'll hear more about this in some later talks. So that was one of the first ones. This was actually where I was joining in again in this enhanced ideas with Anton Melit and Dupay. We have made some really non-trivial equivariant intersection number computations. We computed the equivariant Euler form between these Lagrangians and these Dirac bundles, and we found the very surprising matching on the two sides. Why it's very surprising, because the computation was really, and still it's a bit. We will have to understand that this more. Why this works like that. Anyway, and then what really got me into this was this conjecture of Shaposhnik and Varaya, which was partly motivated by Nigel's observation. They noticed that, and in some other cases too, if you take the real form of a complex group G, then this will give you a Lagrangian, a BAA brane, and its mirror should have support in, that's the conjecture, in the so-called Nadler group of the real form. So the Nadler group is itself a complex reductive group of the Langlands dual of Hitchin. So it's again, unfortunately, a typo. Oh, here it is good. It's good here. Yeah. And that's just, you look at the table in Nadler's PhD, and then you see, for example, U and N is having another group, which is SPM. So that's really exciting, but was for me because it really used the geometric sort of a correspondence over the reals, and still I don't know how this may be possible to be proved, and I am suspicious that maybe it's not even correct in full generality. I will at the end hopefully can say more about this in my last lecture. And then there were many various groups were playing around constructing various branes and trying to match them on their mirror. So there are these BAA, BB mirror pairs, but there are also ABA, AAB mirror pairs. For example, this was Garcia Prada and Hurtubis constructed some ABA branes which are using certain involutions, and then other work of Franco, and Oliveira and Peonieto. They have actually constructed the BAA BBB mirror pairs, which interestingly lives on the singular locus of the Hitchin system. There is also work by Franco and Jardin, where another sort of non-membranes are found in such pairs. So there are several ideas and several proposals of these mirror objects. Okay, so this was about one type of the enhancement where we take into account the hyperkiller origin of our geometry, and then when we take into account the four-dimensional origin that we reduce from 4 dimensions to 2 dimensions, then we have extra symmetry operators. So they physicists propose that the mirror symmetry should be intertwined by these symmetries on the two sides, the Taft or Hecke and the Wilson operators. I will just discuss them in the classical limit. So we will be looking at certain Hecke transformations, transforming a coherent sheaf on the Higgs moduli space. And the problem is, of course, always going to be here is that Hecke transformations typically don't preserve stability. So this is difficult to construct even in the simplest cases when what's so-called elementary modifications. For us, this mu will be a co-character. And then when the co-character is minuscule, then it's an elementary modification. But later we will take any co-character here. So there are purportedly some Hecke operators on one side of the mirror symmetry. This is a BAA operator in the sense, and with Nigel in the paper, there is some sort of argument that a Lagrangian should go to Lagrangian under this operator. And on the other side, we have at least a much more cleaner operator, namely just tensoring with a trihomomorphic vector bundle. So, which is called the Wilson operator, which will be a BBB brane. So what is this vector bundle? And this will be a crucial player in what will follow. So we will take a dominant co-character, a point on the curve, that here we will do Hecke transformation, but here we will do the Wilson operator at that point, and then that with that dominant character, and that dominant co-character will give us a representation of the Langlands dual group of highest weight, mu highest weight representation. And this is a principal G-check bundle, the universal bundle. And then we take the associated vector bundle in that representation, and now we have an honest vector bundle which we restrict to the point of the curve. Now it's a honest bona fide vector bundle on the whole moduli space, and it turns out to have a hyperhomomorphic structure, and then tensoring with it will be the Wilson operator. So yes, I'm just writing down what each check is then. Okay. So now what does this intertwining means? It means that these two symmetry operators should intertwine the mirror symmetry in this sense. If I first apply S, then apply the Hecke transformation, should be the same as first applying the Wilson operator and then applying the mirror symmetry. Okay, so what today, what I am going to study is the simplest case of this intertwining. I will test this for the structure sheaf on one side for the Langlands dual moduli space. I will take the structure sheaf. It is one of the easiest coherent sheaves. And then we will apply this intertwining symmetry to it. So if I try the left-hand side, then I will first take the mirror of the structure sheaf. In the mirror of the structure sheaf, we can use this heuristic that generically this is a fiber-wise Fourier-Mukai transform, and the structure sheaf of an abelian variety goes to the skyscraper sheaf at the identity element on the dual abelian variety. So when you do this in a family, you would expect that the mirror is going to be the structure sheaf of a section of the Hitchin map. This will be the Hitchin section, which is the collection of all the identity elements of those abelian varieties. Yes, and on the other side, what do? We first tensor with this vector bundle and then take its mirror. So the right-hand side is very clean. I have this very nice universal vector bundle. And then I am just trying to think, what is its mirror? And then the answer is that it should be the Hecke transform Hitchin section. So that's why we will first start studying the Hecke transformation of the Hitchin section, because by this philosophy, this should give us the mirror of this universal vector bundle in this irreducible representation. Okay, so then this is going to motivate this study which we started to do, which we did with Nigel. We studied these upward flows in the Hitchin moduli space, which in the next slide I will explain. And for this heuristics, why it will be important, because it turns out that the Hecke transform Hitchin section will be supported at the union of these Lagrangian upward flows. Okay, so now we arrive to this joint work with Nigel.
Tamás, what do you mean by the Hecke operator is BAA?
That it takes Lagrangians to Lagrangians. There is some weak form of this is proved in the paper. So I mean, because weak form, because as I said, Hecke transmissions don't preserve stability. So But by and large, we proved that if you take some Lagrangian here, then it will be Lagrangian there.
W0 plus was the Hitchin section, right? Or
This you will see. This will be as the Hitchin section. It will be a very particular upward flow, which will be the Hitchin section. And this is the structure sheaf of the Hitchin section. And we will start to do Hecke transformations in the today. And next time we will only do elementary Hecke modifications, so that the simplest ones that you may have seen if you have studied Hecke transformations, that we will take a subspace in the case of GLN bundles in the fiber of the vector bundle at that point of k-dimensional subspace, and we will do a modification of the vector bundle, and we will have to do one which preserves the Hitchin section at that point. And then you will get a new Higgs bundle. And then what we managed to understand in the paper with Nigel is that when you do Hecke transformation on the Hitchin section of this particular kind, then you will end up in another upward flow. So let me first explain then about these upward flows.
Sorry, will you
Yeah.
take this as a definition of what is the mirror of rho mu of the universal bundle? Or there is actually something you...
This is all heuristics.
Okay.
There is nothing really well defined. S is not really well defined. It's not going to be so simple, even in this classical limit. Now we understand that at the singular points, all kinds of modifications have to be done on the category. And as I'm mentioning, this is not really working because Hecke transformation doesn't preserve stability. So it's very sketchy, what I am saying. I mean, with Nigel, we always make sure that the kind of Hecke transformations we do that will not leave the stable locus. It's crucial in the paper, but that's a pain to do. But yes, so this is not quite well defined. This one is well defined. So this vector bundle is nice, and this is hyperhomomorphic. And then you will see that somehow this will know a lot about the representation theory of this irreducible representation of the Langlands dual group. And we will use this geometry on the other side to gain information about the representation. Okay, so the Lagrangian upward flows in the modular space of Higgs bundles. So for now on, I will be a bit more specific. We will take PGLN Higgs bundles, which is given by Rankine vector bundle, modulo tensoring the line bundle, and the trace-free Higgs field with values in the canonical bundle. And then the Hitchin map, in this case, takes the explicit form of computing the characteristic polynomial of the Higgs field. And the values and the coefficients of the characteristic polynomial will be certain sections of these powers of the canonical bundle, because the Higgs field had values in this canonical bundle. Okay, so that's the Hitchin map in this case. And there is one more structure which we use all the time, is a C-star action on the modular space of Higgs bundles, which is easy to define. It just acts by scaling the Higgs field. But this action has very nice properties. As I mentioned, the modular space is not projective, but somehow semi-projective, in the sense that the C-star orbits will not be will not have a closure point at both ends, but at one end, when lambda goes to 0, they will have a closure point plus the fixed point set. It will be projective. So these two properties is what we mean by semi-projective, so that the limit point exists when lambda goes to 0. When I close down the C-star orbit at 0, that limit always exists, and the fixed point set is projective. So, okay, you can prove this, by the way, by the property that the Hitchin map is proper and C-star equivariant with positive weights in the base. Okay, now knowing this, we will have a very nice decomposition of the modular space to these Lagrangian upward flows. So what is such an upward flow? So I take a fixed point, C-star action, and take all the Higgs bundles whose downward limit point is this fixed Higgs bundle, and I call this the upward flow from the point E. And because all of this exists for any f like this gives us a decomposition of the space. And the strata themselves have very nice properties. So this is the same Bialinski-Virula, which we have already heard in the previous talk. And so the strata are locally closed subvarieties, which are themselves just a cell, a vector, isomorphic with a vector space. And in fact, even as a C star invariant vector space, it's isomorphic with this C star space, namely the tangent space at the point E, and then we take the positive weights from the C star action on the tangent space. And so that's part of the theory that this locally closed cell is modeled as a C star variety on this vector space. But unfortunately, and that's the crucial point, is this is not a canonical isomorphism. And one more property we have is that the symplectic form is of homogeneity 1. And because of that, one can prove that the upward flow is actually Lagrangian. That says that all these plus the positive part of the tangent space will be Lagrangian. Somehow a weight I place will be paired with 1 minus I weight space by the symplectic form. So we have these Lagrangians, and now because of the semi-projective property, we have a very nice decomposition of our variety into these Lagrangian cells, of which a C star, even we understand them as C star manifold varieties, these cells. But it's clear that it's going to be interesting, those ones where the upward flow is closed. So it turns out that the upward flow is not always closed, so it's not a foliation, but generically, in some sense, it is closed. And we call such a Higgs bundle very stable. So a Higgs bundle is called very stable if its upward flow is closed. It's equivalent with various things. For example, it's equivalent with the Hitchin map restricting to the upward flow as a proper morphism. Of course, if it was closed, then a proper morphism will restrict the proper morphism, but it's an if and only if statement. For example, now you have a proper morphism between affine varieties of the same dimension, so it has to be finite. It's C star equivariant, so 0 will only go to 0. And finally, what it means is that the upward flow contains a unique nilpotent Higgs bundle, namely E itself. The intersection of the nilpotent cone, which is the preimage of 0 here, will be a single point under this map. And this was, in fact, the original definition of a very stable bundle by Lomon and Greenfeld. Okay, so now we have identified the very nice upward flows. And we will see that they play an important role in this mirror symmetry business. We have certain upward flows, which are very stable, will have very nice mirrors. But at the same time, we will also solve another problem. We will be able to find somehow very nice coordinates on the upward flow, so that we will be able to describe the Hitchin system explicitly in these situations, at least in some of these very stable cases. Okay, so that's about the general story about upward flow, Lagrangian upward flows. And let me now show you some examples of very stable upward flows. And these will be the main players in the next lecture on Wednesday. So they will look very simple, but they will look also very Higgs bundle-ish. So unlike the original very stable bundles of Lomon, which he has studied in 1988. So he looked at a vector bundle and he called it very stable if in the cotangent space to it, that is to say the space of Higgs fields, did not contain a non-zero nilpotent one. That was his definition of very stable, but in our language, this means that the upward flow from this Higgs bundle has a single nilpotent Higgs bundle in itself. Therefore, the Hitchin method restricted to it will be finite and proper, and therefore it will be very stable for us as well. But instead we look at the other extreme of the Higgs moduli space. Namely, instead of this is a type n fixed point of the C direction, we will look at type 111 when the Higgs bundle splits into the direct sum of line bundles. Okay, and here there is a very recent result by Anna Nieto, and she managed to go on, basically continuing from Lomon's case, which is n type n, and she managed to completely classify. Now it's more interesting and more complicated than Lomon's result, where she showed that there is generically it's very stable, but she classified which components contain very stable Higgs bundles. But we will be looking at these other extreme to this. So this is still very close. I mean, this is two vector bundles, and we will have n line bundles. So first, the easiest of the line bundles, vector bundles, will be this direct sum of line bundles, the trivial line bundle, and then the inverse of the canonical bundle, etc., up to this power of the canonical bundle. And then this vector bundle is chosen so that the companion matrix of a characteristic polynomial defines a Higgs bundle. So here is the companion matrix of a characteristic polynomial. And then these vector bundles are exactly chosen so that this will fit together to give us a Higgs field. And right, so this gives me an example of a non-trivial Higgs bundle. Over zero, it's actually a famous one. So when there is no, all the AIs are zero, that's an nilpotent Higgs bundle, and that's called the canonical uniformizing Higgs bundle. It's somehow, in my mind, it's on the top of the nilpotent cone. That's the very top. And then it turns out that these other ones, where you allow for any base in the Hitchin system, this companion matrix, it will give precisely the upward flow from this canonical uniformizing Higgs bundle, which is nothing else but the Hitchin section. And in fact, Nigel observed this when he constructed the Hitchin section, that this space has to be closed, the Hitchin section. And so that actually shows that the canonical uniformizing Higgs bundle is very stable. So on the top, we have a nice, very stable upward flow. So now we are going to do elementary modifications, the simplest kind of Hackett transformations. And so at the point C, we will do we take a k-dimensional subspace inside this at the point C of this vector bundle. And then we have to twist these line bundles appropriately so that this Higgs field, which is the same Higgs field as before, except that the case position, the one we replace with this section of this line bundle, which vanishes exactly once at the point. And then again, these twists are chosen so that they will fit together to give us a nilpotent Higgs bundle. And this Higgs bundle will turn out to be the Hackett transform of the canonical uniformizing Higgs bundle. The case fundamental Hackett transformation is going to be this. And with Nigel, we have a complete classification of the very stable type 1,1 Higgs bundles. So in particular, it applies to this one as well. And then we can show that this is also very stable. The proof retrospectively, I mean, we have a non-trivial argument there, but retrospectively, we can argue that what we have noticed is that the upward flow from this case Higgs bundle, this from this guy, is nothing else as the elementary Hackett transformation of the Hitchin section. And then, of course, that was closed, so the Hackett transform thing will also be closed. But okay, at the end, we will be thinking about more complicated Hackett transformations. And what's special about these Hackett transformations, that their space inside the Hackett transformation space is already closed. So and that's because it's a minuscule co-character, or in this case, character of the Langlands group. Okay, so that gives us examples of very stable Higgs bundles. And what I'm going to do next time, I will understand these upward flows, the Hitchin map on them explicitly, but I have motivated on the previous slide in terms of the equivariant cohomology of Grassmannians. And then when we will do mirror symmetry on them, we will get these universal bundles in these irreducible representations that will relate to certain Kirillov algebras. And then I will also explain how the BNR correspondence naturally appear from the. But because I still have maybe a bit of time, I start then a bit more. I put one more slide at the end. And that's in itself kind of an interesting way to measure proper maps between Fi spaces of the same dimension, which are C-star equivariant.
Tamás,
Yes.
in the formula for the Hecke transform, which bundles are twisted by C? It seems that some are, I don't know.
Yes, I believe that you take the last n minus k of them and that you have to twist, and the first k you don't. I hope it's correct. I mean, I try to make it correct, but yeah. Yes. Okay, so and because I always like to compute some, so I always like to have some measurements of the objects that I study with, and this is what will be understood here. We will talk about the equivariant multiplicity of these proper maps with these upward flows, and then there will be a natural notion of a multiplicity algebra. And that's what started off actually the progress which I will talk about in the next lecture. So let me talk about how to define the multiplicity algebra of the Hitchin map restricted to a very stable upward flow. So the multiplicity of such the Hitchin map, so here is my upward flow, it's very stable. That means that this is a proper map, C-star equivariant proper map. And it turns out that there is a very simple-minded but very nice algebra one can attach to such a map. Both of them are Fi spaces of the same dimension. So you just have n functions, and they are all weighted homogeneous. And then you can define this multiplicity algebra. Okay, geometrically speaking, it's the scheme theoretical zero fiber, the preimage of zero. It will be not just a point, but it will be a fat point, and the coordinate ring of the fat point is going to be the multiplicity algebra. But you can be very explicit. You can take just the ring of functions on the upward flow and divide by the preimage of the Hitchin map of the origin there. And again, even more explicitly, it is just this. You take the polynomial in n variables. These are some coordinates here. And then you take your Hitchin system in this on this vector space in some explicit form, and you just take the ideal they generate. So it turns out to be a complete intersection in the very stable case. So this notion, I was very surprised to find in early works of Arnold, in the Arnold School of Studying Singularities of Manifolds, and they prove some wonderful properties of this, which was basically the starting point of the things to come. So let me just recall them. So this algebra is finite dimensional if and only if this map is proper. So if and only if we are in the very stable case. Which for us means that it's very stable, that it intersects the nilpotent cone in a single point. In this case, the dimension here is what we call the multiplicity of this map, the lengths of the zero fiber. Moreover, this Hitchin map is C star equivariant, so there will be a C star grading on this algebra. So C star will act on the multiplicity algebra, and so you will have and this will be a graded algebra, and here will be some gradings. And the top grading will be one-dimensional, generated by the Jacobian of the Hitchin map in this coordinates. The pairing between opposite degree parts will be non-degenerate, so it is what we call a Poincare duality ring. I already mentioned that basically by construction it will be complete intersection, so Poincare duality follows from that, but they also have proved this pretty elementary, beautiful way. And finally, you can compute the Poincare polynomial of this graded algebra by some very simple computation at the infinitesimal information at the tangent space and the base of this map. That Poincare polynomial is what we, with Nigel in the paper, we already have defined this without knowing all this beautiful geometrical understanding. We just defined this as an equivariant multiplicity. We proved that this is monic and palindromic, but both of them follow from this much richer structure of this finite dimensional complete intersection algebra, Poincare duality ring. And then what then became the quest once we have identified this algebra is can we understand this multiplicity algebras explicitly?
So by the Jacobian of H(E), you mean like the derivative of it?
Yeah, the usual calculus
Okay.
notion of the Jacobian. This is pretty simple-minded. I find it amazing that this is kind of a hardcore commutative algebra, but they are topologists or differential geometers, and they have completely understood it explicit analytical terms. Okay, and I just mentioned here that Nigel had studied this for the case of AE0, so not for the type 1 case that we will do next time. And then he found some amazing properties, for example, that his multiplicity algebras vary in a continuous fashion, so they have a moduli. And that was, it's really, really interesting and also super hard. So he could do genus 2 and 3, because in those cases, I don't know, the geometry of the Hitchin system can be explicitly understood. And it's already very complex. But also, we will see that up there for type 111, these Poincare duality rings actually will be sort of cohomology rings of varieties. In particular, they will be integral. And Nigel's rings are not integral because they vary in a continuous family. And somehow geometric Langlands and then the real Donaghy-Pantev version of that is somehow placed here. So I think what Nigel is looking at is really where the real difficulties are. But what I will show you that if we do all these studies on the top of the real form at these type 1 fixed points, then we can actually have a complete understanding, almost complete understanding of these multiplicity algebras. So that I will do on Wednesday. Yeah.
Hey, yes. Yeah.
Does something like this multiplicity algebra arise on the mirror side as well?
Exactly, that's what I will discuss next time. So, okay, this multiplicity algebra so far lives on the upward flow side, on those Lagrangians. And what I will be able to do next time to find this algebra inside the irreducible representation on the universal bundle on the other side. But these algebras at the very end, these big algebras, and somehow even more complicated versions of these multiplicity algebras. And right, but they will always satisfy Poincare duality. Conjecture, they are always complete intersections. Yes, but I will not be able to do all the geometry. You will see. You will see.
Any other questions? Okay, so we have a coffee break until 4, is that right? Okay, thanks again.